Let's simplify some more Boolean expressions. So what we see as outwardly apparent here is that we could use De Morgan's to break up this large inversion bar and this large inversion bar. So let's apply De Morgan's theorem 16 and 17 to these. We have to keep this term the same, change the sign, and write the other term, at which time we could break up those inversion symbols. Again, here I keep this term and this term the same, but I change the sign from and to an or, allowing me to break up this bar. That's what De Morgan's lets us do. Now I see that I have a double inversion and a double inversion, which of course is just the signal itself, according to Theorem 18. And I remind you to please have your midterm formula sheet in front of you so that you can follow along and know which theorems I'm referring to. And now I see an opportunity to do De Morgan's again here. So I'm going to take both of those signals, A, B, change the sign to an or instead of an and. That lets me break up that sign, but I caution you to keep your brackets because that's still ended with a C. Now I can distribute here, which we said that's theorem 13a. And when I distribute, I get the following. Always keeping alphabetical order. Now I would tend to distribute this again to see what I get. So here I'm going to distribute here, 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 and here. So I'm expanding. And I hope you know how to do this from math class. And now I need to remember that this looks familiar. CC bar, in the CC bar here, A bar. Now this is an AND gate. If one of them comes in as a straight signal and the other one is the inverse of the signal, then one of them must be a 0. And anything through an AND gate that includes a 0, of course, is going to become a 0. And that's theorem, which theorem is that? That is going to be, that's theorem 4 again. And that leaves us, I'm going to write an extra step in here that you might not need, but that leaves us with a 0 and C bar Now we have to look at, well, what does it mean when something is ANDed with a 0? This is ANDed with a 0, this is ANDed with a 0, ANDed with a 0. Anything ANDed with a 0 is going to be 0, and that's theorem 1. Anything ANDed with a 0 becomes 0 itself. And I'm putting lots of extra steps in here. So I'm going to end up 0 plus the term 0 plus the term 0. And now I need to look at what anything ORed with 0 is. And we have theorem 5 that says anything ORed with a 0, the answer is that anything, which means that the answer here is A, B bar, C bar. And that is very nice, but I'm looking at my paper and got a different answer. I got A bar, B, C bar on my paper. So now we're going to go through a nice educational exercise about figuring out if there's a mistake here in this lecture. There is. I transcribed wrong. Here is a B and then there's an A. All right, my apologies. Sorry to raise anxiety on those of you who are following along. So we're going to have to make a correction here. This should have been a B. Which means that this would have been so this would have been B, B bar C. So it would have been one that I need to circle and go to 0. And this one here would have been A, B, C bar. A, B, C bar. So A, B, C bar. This one would have been okay. This one would have gone to 0. All right. So then this one would have been A, B, C bar. And this one would have been B, B bar, C, which would have been 0 going to C, which in itself becomes 0. And I hope that the astute student is following along correctly here. Oops. And all of these are or with 0, therefore the answer is in itself the same as before it was ORed with 0s. And that is the correct answer. Sorry for the error there, and thank you for following along. That's question 4. Look at the questions that we've already done. Okay, so let's do one. That was a big one, so let's do one a little bit smaller. Let's do this one. Let's do an X and a Y, inverted before an and, inverted after the and, multiplied by X. What I would do here is I would use De Morgan's. I have to change the sign, then I can break up that large inversion sign. That's one of De Morgan's, it's number 17. And then I would recognize 18. Theorem 18 says that two inverted bars just are the same as just the signal itself. Then I would distribute using 13a, and I would say well, that equals x times x plus xy. And then I would say, well, x ANDed with itself, the answer, if it's two ones, the answer would be 1. If it's two zeros, the answer would be 0. So it must be x. And then, so that's theorem 3. So x, the answer here is x. I cannot type on this screen. The answer is x plus xy because of theorem 3. And then we have interesting theorem 14. Theorem 14 doesn't come up a lot. Theorem 14 says x, it literally says x plus xy equals x. So the answer is actually x. That's a very nice question. I like that one. So that's question 5. Let's do another example. Let's go back to A, B's, and C's. And these are chosen arbitrarily. It doesn't matter. Actually, I like this question. Let's do x ANDed with y inverted and z inverted plus yz uninverted, all inverted. Well, I'm going to first use De Morgan's. Actually, you know what? Before using De Morgan's, I'm actually going to expand. I'm going to use 13a. All inverted. Then I'm going to use De Morgan's. De Morgan's 16. I need to change the sign. Therefore, I can break up this big inversion bar. And then in each of those, I'm going to apply De Morgan's again. I need to change the sign. And then I can break up the inversion bar. Again, I need to change the sign. I can break up the inversion bar. Now I recognize, so sorry, that was 17, De Morgan's 17. Now I recognize theorem 18, which deals with those double inversions. And now I need to expand. That's 13a again. I'm going to expand. When I expand, I'm going to get a rather large expression. Okay, so I got this rather large expression, and then I'm going to recognize in that expressions theorems such as this y inverted and y. Well, one of them is a 0, one of them is a 1. So these are going to go to 0 because they're through an AND gate. That's theorem 4. So that's going to leave this expression. And I'm going to then factor out x bar because I see that in a lot of the terms. So I factored out here, and factoring out, I think that's a 13a again if I go in the factoring direction. And then I recognize that I have a y plus a y bar. So here I have a y bar plus y. And do I have a z bar plus z? Yes, I have a y bar plus a y here. Let's just deal with that one. If I have y bar plus y, then that would be equal to 1, and that's theorem 8. So then let's rewrite that with the plus 1 instead of y bar plus y. So then I'm just left with one y in there. And I'm going to, what can I do here? I paused the video there for a minute to correct a little bit of a typo that I made. Here I had XY, but it should have been XZ. So transcribe through, then, sorry, X bar Z. Then when I take that X bar, here's the Z that I was missing in there. And now I can see that I have another expression here, Z bar plus Z. And if I, that expression will be the same as 8, as is also governed by theorem 8. Z bar plus Z is equal to 1. So then that'll be another 1 in there. So carrying on and substituting 1 for y bar plus y and 1 for z bar plus z, then I would have x bar times x bar plus 1 plus another 1. So or 1 or 1. And then the rest of the expression y z bar plus y bar z. And at this point, we need to recognize that 1 and 1 equals 1. 1 and, oh, sorry, 1 or 1 must equal 1, because that's governed by theorem 3, where x or x equals x. So then we would get x bar times x bar just simply plus 1, plus the rest of the expression. And anything ORed with a 1, the answer is 1. So anything ORed with a 1, the answer is 1. And that is expression 6. That is theorem number 6. Says anything ORed with a 1 has the answer 1. So now our answer is x bar times 1 and 1. So here is our expression. And now I've come to my next question, where x bar and 1, anything ANDed with a 1 is just it itself. So that's just x bar. So that is governed by theorem 2. And now we can look further and see if we can find any other theorems in here. Sometimes 15 and 16 are interesting ones. So I'm not seeing theorem 15 or 16 in there. And let's see what happens if we factor out. Oh, I can't really factor out a y or a z from there. I think this might be as far as we can go with this expression. I don't think I can simplify this expression any farther. Yeah, I'm going to call that the final answer. So that was quite a long one. We used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 theorems, some of them repeated in question 6. So I hope you enjoyed question 4, 5, and 6, and painfully working through these together. You can see that they take a lot of steps, just like the math that you're used to.